Three problem, and the first one by Hiroshi Yokoyama from Kent State.
Good afternoon, everybody. It's my pleasure to be here, and I'm very grateful to the organizer for inviting me here. And it's a great time for me to learn a lot. And I'm going to return to the subject matter of the discussion this morning. It's about a really mysterious problem associated with K13, so-called the splay band elasticity. So we saw quite a lot. Do we have a laser pointer here? Okay. Yeah. So there are three eigenmodes in nematic elasticity: splay, bend, and twist. And we also see a K24 term, and this is the last term, K13, 1-3. This is the subject matter of this talk, and it's well known that this causes a lot of interesting, strange behaviors when the straight variational calculation is applied. And this comes from the normal derivative of normal derivative of this term. That makes the whole different thing compared to other terms in the Frank elasticity. And especially, this is quite common in kinetics. If you throw a ball, or we normally specify the position and velocity. So it's not really uncommon to specify derivative in the initial condition problem, but when it comes to a boundary condition problem, it sometimes causes a really serious problem. And in fact, K13 makes the whole variational problem ill-posed or overspecified. That makes the behavior could be sort of arbitrary. In order to minimize the free energy, you can take whatever sharp distribution at the interface so that you can get the free energy indefinitely small. So there is no absolute minimum as long as you keep K13 finite. So it's really problematic, and back in 1997 I published a paper. I worked quite a lot by then, and that was sort of a closure of myself and not everybody. And so after that, I didn't really elaborate, or I completely forgot this problem. And my conclusion was that K13 should be 0. And that's the whole story. And that solves all the problem, and that almost everybody has been taking in calculating the variational structure in nematic elasticity. So it's fine, but at this time Peter asked me to revisit this problem once again. So the title of the talk is K13 Revisited. This is not your revisiting this problem, but my personal revisit to the problem. It took quite a while for me to recover or remember what I did back then. And so I like to share some of the understanding I recovered from my own paper. And it could be wrong, and some of you may not agree. It's fine, but I'd like to mention a little bit about not only K13 equals 0, but also some of the interesting things that I discovered while doing all these calculations. So K13 first introduced through a phenomenological discussion. Frank, Ossin, those people came up with the K13, and some of them just discarded, or some of them kept K13. And the problem persisted nearly 40 years since then, and there are many, many papers published on this problem, and the number of citations I listed is really minimum. There are many reasons why I didn't put so many citations in this presentation, because there's so much controversy went on as regards this problem, and so as a matter of politics, I didn't really cite any of those papers. But when you have a chance to read my old papers, you can find many of the papers published by the time I published that paper in '97. So these two are surface-like. My point is that K24 term, subtle play, is a real physical existence, but K13 is a mathematical artifact. And there are a couple of attempts to solve this problem in practical cases or theoretical background, and I don't have enough time to go in any detail of these ad hoc things. So this is my conclusion, K13 equals 0. So even though phenomenological gradient expansion of the free energy generates a term, apparently that is K13, but microscopic constraints could provide an additional result, and that is actually K13 equals 0. And this is pretty common in elasticity. In old days, Cauchy developed a microscopic theory of elasticity, and they found a relationship between elastic constants that couldn't be reached simply based on the symmetry argument. So this is not uncommon. Microscopic theory can give us additional information about the fundamental properties of elastic constants. And so, as I wrote here, we can learn actually a lot about the local behavior of pneumatics by looking at the elastic behaviors. And in fact, in the 19th century, Cauchy encouraged a experimental study to compare the microscopic relation he came up with and the experimental results to infer the microscopic origin of interactions acting in condensed matter. So there are two plots in this talk. The first is the proof, or I'd like to prove K13 equals 0. And it is almost trivial if we assume a ground state is uniform. This is almost a synonym that K13 should be 0 if we assume a ground state is uniform. Like I said at the beginning, the paradox indicates that when K13 is finite, the lowest energy distribution should be deformed. If we make a constraint that everything should be uniform, that automatically ensures K13 should be 0. So this is not a really interesting assumption from which we can develop our proof. So in order to go one level deeper, we need to allow a distorted ground state. And in the case of a chiral system, chiral pneumatic that develops a hierarchical structure spontaneously, that is exactly what a spontaneous distorted state is all about. And so based upon the Frank elasticity and allowing the ground state might be deformed, we also can discuss the chiral structure as twisted pneumatic does have. And K13, when we work out a microscopic expression based on density functional theory, it involves a redundant parameter, and that is a sort of a microscopic gauge. And that gauge dependence is exactly the manifestation that the K13 is an artifact, not a real thing. Plot 2, this is density correction. And historically, there are many theoretical papers with an attempt, with the purpose to develop microscopic expression for Frank elastic constants. Most of them, particularly a mean field theories, assumed even if the nematic is deformed, as long as the deformation is weak, locally the distribution function is exactly the same as the equilibrium nematic. So this local equilibrium assumption is a pretty strong requirement, in fact. This is what I'm going to show. And as soon as you relax this assumption, we immediately see that there must be a correction in density function that accounts for the change of local distribution from the local equilibrium. And that, in fact, gives rise to a distribution function at the bottom. Perhaps you are immediately aware that this is exactly what fellow flexoelectricity is about. So please remember that when we talk about flexoelectricity, it's exactly the change of the distribution function. So by deforming the system, the distribution function should be different from the equilibrium. And the elastic true microscopic treatment of elasticity should be able to tell something about those local change of distribution function. So this is the number 2. And I'd like to cover these 2 plots. So let me begin with the phenomenological construction of nematic elasticity. And this is just a standard thing. We think about the gradient of a director. And in terms of the amplitude of variation of director, in terms of the wavelength, characteristic wavelength of change, it is of the order of epsilon over xi. And this second order derivative is epsilon over xi squared. And what we're going to try to do is to keep the free energy expansion up to the order of epsilon squared over xi squared. So formally, this is what a phenomenological development does. And using these terms like this with coefficients that have a compatible symmetry with respect to nematics. So nematic should be apolar and should appear twice all the time. And we can develop a proper symmetry tensor like this, and we put everything into this formulation and coming up with the Frank elastic constants K1 up to K13. Now, so in order to say something more concrete about the microscopic behavior of nematic elasticity, I employed a density functional theory. Quantitatively, density functional theory is not such powerful as a theoretical background, but when it comes to a formal development of the rigorous expression, this is so powerful and rigorous, and as I'm going to talk about. So it is essentially a ground thermodynamic potential considered as a functional of local density function rho. And let me mention a bit about the internal structures. This part is ideal gas part that doesn't have any interaction. This part takes care of the interaction, and this is a chemical potential. This is external field. And a really nice thing about density functional theory, originally this was developed for quantum mechanical calculation of electron clouds in condensed matter, and then applied to liquids. And everything I'm going to talk about was adopted from this paper. And the really strong, nice thing about density functional theory is that as a functional of rho, ground potential has a minimum property that takes a minimum at equilibrium distribution function. The proof of that theory is pretty straightforward, starting with this distribution function for n particles and with Hamiltonian Hn. And this is a standard distribution function. And trace is just a classical integration over the phase space. And let's consider a functional as shown here. Hamiltonian chemical potential part, and this is the entropy part, and take a trace with F, and it's immediately clear that omega F0 is exactly the equilibrium ground thermodynamic potential. And the fact that this functional takes the minimum value at the value of at the distribution of equilibrium comes from this equality, and this is a very famous Gibbs inequality thing. So this is always positive for normalized distribution function as long as f is not identically equal to f0. So the inequality is then proven. And using the Hamiltonian, that is simply kinetic energy and a potential energy. And what is really good about density functional theory is that we don't have to assume any form of interaction energy, pairwise, or just an n-particle interaction is fine. And V is the external potential. That is essentially a single particle potential exerted on the system. And this is the density operator. Equilibrium density is just a trace of density operator. And these are all for simple liquid, but we can easily extend this to a more complex liquid like liquid crystals. So the density functional recipe is something like this. Take an arbitrary density, and there is a unique external potential Vext that makes the given density function the equilibrium density. And that external potential determines the equilibrium probability F0, and then we can find a functional that corresponds to F0. So using that F0, then we can define unique functional ground thermodynamic functional of rho that reads something like this: external potential, ideal gas part, and chemical potential part. And the variational principle is simply the functional derivative of this functional must be 0 at the equilibrium density. So specifically, all of these are given, and in non-interacting case, it simply gives the Boltzmann distribution particles existing in external potential VR. So the whole thing can be viewed as a very simple spring model. Everybody knows that the potential energy of the spring with a mass is given by 1/2 kz squared in gravitational field mgz. And what a variational density functional theory does is to calculate this functional, in this case the functional of z, for the case of a multi-particle liquid systems. So what it does is exactly the same. Here we see that this part is the equilibrium ground thermodynamic potential that is represented by omega b rho, corresponding to the given arbitrary density function rho r. And in order to come up with the original functional of rho, we simply need to add the difference of potential between the initial one and the last one. Last one means this is a unique external potential to make the given rho r the true equilibrium of the whole system. So if you know the equilibrium ground potential, you can just construct the whole thing by adding external work that is necessary to deviate the whole system to what you are looking at. So this is basically what density functional theory is all about. Normally, people just take the expansion and take a virial expansion or something like that, but I do not take that approach at all. I'm just interested in what this rigorous framework can tell in terms of K13 and elastic properties of pneumatics. So this is naturally comes direct correlation function. There are a whole series of hierarchy of direct correlation functions. The first one, this is the interaction part, functionally differentiated with respect to the density function. This is lowest order direct correlation function. That actually is the local chemical potential, including the interaction part. And this is the second direct correlation function, 2-point r omega r prime omega prime. And there is, because you can change the order of differentiation, there is a symmetry in terms of the change of variables. So free energy density. And so we are interested in how the whole energy, free energy changes when the pneumatic is deformed. So we need to compare the initial state, whatever initial state is taken, rho 0, that is deformed, to give rho deformed, and we calculate the difference of these two ground potentials. And in fact, the goal of elasticity theory is to come up with a free energy density, elastic free energy density, which is a single point function, R. This is very important because this is a multi-point functional. This is just a single function of R integrated over the whole volume. So transition from this multi-particle situation to single point function is really, really a critical point to prove what K13 is all about. So the whole development is a little bit complicated, and so I try to take only the essential part. And here we have a Goldstone mode in pneumatics. When you rotate the whole thing uniformly, there shouldn't be associated with any increase in energy. So if you uniformly change n to n prime, the energy change must be 0. And if we take a derivative comparing the initial state and last state, and we can put in this result in the initial condition of equilibrium, and that gives this one. And going up to the higher order, one level higher order, we get this equation in terms of the direct correlation function as defined here. So the right-hand side, this expression must be of the order of square delta n. Shouldn't be exactly
will you disregard the direct or dependence in direct phase correlation? Because the direct phase correlation should depend upon reference state, which if it's pneumatic, then it should depend upon reference disordered pneumatic. So it should be direct or dependent, and it should produce extra terms as well.
I'll let you.
Yeah, homogeneous. That's what I mean.
So no gradients.
Yeah, no gradients, but,
Yeah,
but there is the director.
Yes.
Yeah.
The direct correlation function itself doesn't need to have any reference. It's a state correlation function. But when you employ any series expansion, you need a reference. And the reference state may be chosen arbitrarily, but there is a good selection that makes the whole thing easier. So this is what exactly what I do in order to make the whole thing less approximate. And using the reference, whatever reference that is connected to the last distribution function by means of a parameter alpha in this simple way, and you can just take a derivative and integration so that you can formally make a series expansion in the order of the difference of initial and reference and the last density function. So by repeating the same process over and over again, you can just formally develop a series expansion. And the reference density should be arbitrary. So you can choose uniform distribution in pneumatic. You can choose isotropic phase. That's what some people did. And so up to second order, we can come up with something, expression something like this. We have a difference of density function here with a direct correlation function. The rest is a higher order term. And this is the key expression. As long as we assume a uniform ground state, this is really key. And we have a density deviation from second order here, 1 and 2. And here is a direct correlation function. And we're going to evaluate. This has nothing to do with K13, actually. As I said at the beginning, this formulation gives K13 equals 0 immediately, because this is almost a synonym of K13 0 equals 0, and uniform ground state. So as long as we assume uniform ground state, K13 is automatically 0. But in order to show you how the other elastic constants can be expressed in terms of direct correlation function, I'm going to work this out. And this second order thing can be decomposed into more convenient form, and only third term can contribute to gradient expansion. And here we see a same angular variable, and the position is different. So we can simply employ gradient expansion. And other terms doesn't create any gradient term. Or other terms also vanishes because of the Goldstone degeneracy. So molecular expressions for Frank elastic constants. We define a tensor in terms of direct correlation function and the derivative of initial uniform distribution function given by n0 director and angular variable that is basically pointing the long axis of molecule. And this is again derivative, and U means the separation between 2 points, and omega k and omega l. So this fourth rank tensor is given by 2 u's and 2 omegas. And assuming that z is parallel to n0, the original the orientation, then we can easily reconstruct that k11 equal m x x x x. And those are the results that we get for K1, K2, K3, K24. And like I said, K13 is a inevitable result of this development. So this is the lowest order approximation. And here we see that we already see a relationship between K24 and K22, K11, depending on the matrix property, specific expression of matrices.
Clarify, please. I mean, why in this case K13 is not obvious? Because this should be a particular entry to this fourth rectangle, right? And which
Yes,
one?
that's right. And this expression takes care only of second order derivative. And K13 as a deforming agent, it should come from the first order term.
There are two gradients there. So it should be the part of the same tensor. It's not a linear gradient term, it's a quadratic gradient.
This simply comes from the second order term that is contained in the first order expansion. And so the initial paradox argument, the K13 non-zero K13 works only when the whole system is not uniform, only when the director makes a steep change at the interface. That is the less energetic state.
Why then K24 is non-zero? It's the same type of term.
Yes, I have something to tell you later. Actually, contribution to K24 comes both from first order and second order.
Does K13 correspond to one of the matrix elements of M?
No. No. So K13 is inherently not present in this level of expression. And in order to come up with a molecular expression for K13, we have to deal with the first order expansion.
Hiroshi, is there a reason? I mean, these K11s, K2s, are obviously, they're inherited from elasticity, aren't they? I mean, the notation is inherited from elasticity.
Right.
And so the K13 is presumably also inherited from elasticity.
What do you mean by inherited but from elasticity?
Yes, but K13 comes from a tensor that has more than 4 indices. Right? These are all the 4 index tensors.
Yes, no, I was trying to figure out what the logic here is. That's
From the
all.
B tensor that introduced before.
Well, in fact, K13 comes from the third rank tensor, not fourth rank, and that is associated with the first order expansion of the free energy. And so let me continue. And this is the Cauchy relationship that is found at this level of expression. And that comes from the symmetry relationship among the matrix elements. And the assumption we use is that the locally, even in a deformed nematic state, the local distribution is the equilibrium distribution. So that is essentially the basis of this Cauchy relationship. Back in '71, Nering and Sapit developed a molecular theory based on mean field model, and they came up with this Cauchy relationship. And their assumption, being mean field theory, it contains many assumptions in it. And one of them is the local equilibrium assumption, using the same distribution function as in the uniform nematic state.
So usually Cauchy comes because you have an elastic constant which is 4 G's or 4 X's in a row, and it's symmetric with respect to interchanging IJ, NK, L, and all of them symmetric with respect to interchanging everything. Your density functional M isn't, because it has UU and omega omega.
Right.
So
Yes.
it's not clear that how that's fun. See, that thing is symmetric under I and J interchange and K and L interchange, but not under IJ, KL interchange. So how do I see the K24?
K24, there is a, this is symmetrical in terms of XY change of YX.
Yeah.
And originally, K24 is a sum of XY, YX, and XY, XY.
Yeah.
And when we compare that expression with K11 and K22, we can show that Cauchy relationship.
That follows obviously from your expression for M.
Yeah. So at this level, Cauchy relationship holds because of the local equilibrium assumption. And I'm going to show you this is just approximate. So we need to go one level deeper, but before that, let's discuss a density correction beyond the local equilibrium assumption. And again, we use this expression with the direct correlation function, and using this as the basis. And we need to evaluate what the difference between true deformed state and the assumed local equilibrium distribution function. And this is simply a minimization of this free energy in terms of delta rho. But we have to be careful to keep the order of this function as high as 1 over design squared. And in order to solve this equation, we can note that we have a Goldstone degeneracy. So whenever we add a form like this, we have exactly the same free energy. This form doesn't consume any energy because this describes the uniform rotation. So we can use a vector A as a Lagrange multiplier. And using that Lagrange multiplier, we can solve this equilibrium problem. And we finally get a solution. And this is what we have, and the solution is given by this equation. So this is the density function correction on top of the equilibrium distribution function. This is the inverse of the direct correlation function. This is the original direct correlation function. And this is the director gradient. And we also have omega and u. And important feature of this density correction is that this is asymmetrical with respect to the inversion of omega. So when you change the omega by 180 degrees, it changes the sign. So density correction function, when it is evaluated in terms of the tensor, second rank tensor components as defined here, we see that jxy, yx, and zy should be 0, and we're left with 3 independent components, and j1, j2, j3. And those terms are actually associated with this splay flexoelectricity or band electricity term. And the final result is that with a coefficient, which can be a function of n dot omega squared, then we have a distribution function as shown here. So this is actually the cause of flexoelasticity, and if you are able to evaluate this integral, then you can come up with the flexoelectric coefficients. So with that density correction, this is the change of Frank elastic constants. Originally, for K11, for example, mxxx should be reduced by delta mxxxx. And similarly, all those constants are subject to some changes. And here again, we have another Cauchy's relation, which states that xxyy equals xyyx. And that is exactly the counterpart of that symmetrical property at the lowest order. So we now have, this is not rigorous, but we can only say rigorously that K24 is not necessarily equal to K11 minus K22 divided by 2. But as long as we assume that the orientational correlation is almost negligibly small with respect to the rotation around the long axis of molecule, the only K11 correction works here because correction to K24 and K22 are related to rotation around long axis. So this one only is reduced a little bit from Cauchy's relation. So it is most likely that we have an inequality like that. Okay, so let's move on to K13. And it must be done from the first order expansion. And these are terms that generate K13. K11 and K22, ordinary Frank elastic constants come from higher order term, second order. So I'm going focus on only on first order, from which K13 is generated. So so what matters here is that the form of this is that we have a this is not really appropriate. It seems that I lost one slide, but so it's actually the result after employing a gradient expansion. And here the gradient expansion is something like we need to deal with 2-point functions. One is associated with r omega, and the other one is r prime. And so always the integration is of the form integration over r and r prime. We have a integrand, 2-point integrand. And so in order to come up with the elastic energy density, which must be a single point function, we have to define how r must be related to 2 points. And there are many different ways to do that. And if we impose a condition that r and u is the difference between two vectors, position vectors. These are give an equal volume integral. Jacobian is just unity. And r, when 2 points are just a single point, r must also be r. And if we shift the position by the same amount, the capital R also have to be shifted by the same amount. So with this condition, what is we're left with is a expression something like this. R is a somewhere in between here with a divided between these 2 points. And when gamma equals 0, this is just middle of 2 points. And by changing gamma, we can change from this side to that side. And in fact, in many papers, people actually took different choice for gamma, some without any good reason. Sometimes they take gamma equals 0, sometimes they take gamma 1/2, so that r is equal to small r. And but in fact, there is no fundamental reason what should be the choice for gamma. So this must be left arbitrary. And with that choice, two density functions can be written as this. Gamma appears here, gamma plus 1/2 here, and we expand up to the second order in terms of the gradient. And after putting that, what we left with is this result. And there are two terms. The first term doesn't involve gamma, so it looks fine. The second term, that involves gamma. And so this is already the surface term. Here is a divergence of a vector inside the parentheses. And this term actually that generate K13. And gamma is arbitrary, and that is the clear indication of the problem K13 has. So in terms of the tensor element xdx, which is defined based on what we saw, xdx, and we have a parameter, arbitrary parameter here. And similarly, K24 is a combination of second order contribution, density correction, and first order contribution. So this term is also involves gamma. So gamma is just choice how we reduce two-point function into single density function. So if the final single function really depends on arbitrary parameter gamma, nobody believes that this is a real physical quantity. So if bxdx is non-zero, K24 is also becomes very problematic. But I'm going to show bxdx is 0. So this is how it goes. And we have a Carnot function here, and this is shown like this. And now we replace r and r prime, and r prime and r is something like this, and we immediately see that by using all those expressions, this Carnot function is actually antisymmetric. So if you interchange these two points, then it gets a negative sign. And the rest is just a higher order term. So with that, the thing is like this. So when you change the variable from r, small r, r prime, to u and capital R, the integration is the real integration range must be this segment of the space. And if you don't care too much attention to what is the real integration space, but just changing the variable from to capital R and U, what people just do is to integrate over U from everywhere, and integration runs from capital R from 0 to infinity. And so after the gradient expansion is performed, the integration actually is being performed the area including this shaded region. And like it said, there is a antisymmetric relationship between G R prime R and G R R prime. So if your integration is such that always the point is symmetrical about, mirror symmetrical about this axis, then you get the cancellation of these two. And that applies to the real space of integration. But if the integration is done over the extended state in terms of capital R, then you end up with K13, which is the difference between A region minus B region. And there is an accidental cancellation of K13 that is in the case of exact orthogonal case, IA equal IB. But in fact, if you're careful enough to restrict your integration to the real integration area, then you simply get the cancellation of these two, and that ends up with the only higher order from which no K13 contribution emerges. So K13 equals 0. And this is what I'd like to say. And I'm not sure if you're convinced or not, but this resolves many of the problems. And also, we saw that K24 involves a term exactly the same as K13. So if K13 presents a problem that is inherited K24 as well, not in the same way as K13, but in a different manner. And lastly, I'd like to mention a little bit more about what I learned by developing this calculation. I split the direct correlation function into symmetrical and anti-symmetrical part. And I dealt with two terms on the first order expansion. The K13 term actually only involves a symmetrical direct correlation function. And that goes to 0. And the other one here only involves anti-symmetrical part. And this one is, after some calculation, end up with a twisting power term, which is linear in the twist. So this term actually gives rise to twisting power of the chiral-pneumatic. So these are things that I learned from all the development of this density functional theory. I didn't calculate any quantitative value of elastic constants, but the only thing I got is K13 equals 0. Thank you very much.
Okay, I'm going to suggest that we don't have questions now. Maybe after Epifanio's talks, if you have two talks on the same topic, we might have some questions at the time. And I also suggest we take a 2-minute break so Epifanio can. I need a break.